Okay, let us start our today's seminar, and our speaker is Kirill Struminsky, who will talk about his recently accepted paper, joint paper with Simon Lacon-Julien and with Anton Osokin, which was recently been accepted to NIPS. So this paper is about surrogate losses in structured output prediction models, whatever it means. So let us listen.
Okay, thank you for the introduction. I'm very honored to give a talk here. As the first words clearly indicate, this is a theoretical work. We have no experiments at all, and we try to provide some learning guarantees for structured prediction problems.
Please share with us your experience of how to get accepted to NIPS without any kinds of experiments.
Okay, sure.
It's very useful for us.
So I hope that all the words in the title of the talk will be clear at the end of the talk. So first of all, let's give an informal introduction in what the structured prediction is. So typically we all deal with prediction problems. We do machine learning and we get input X, and then we want to predict some label Y in discriminative problems. And structured prediction is an umbrella term for the kind of problems where the output label is typically a random vector, which has dependent variables, and thus the label can be a random variable with an exponential support. But at the same time, it has some structure, therefore we call such problems structured prediction. The classical examples of such problems are, for example, image segmentation, where we get an image as an input, and then we want to predict a mask for each pixel, and the mask indicates to which class this particular pixel belongs. So the output is exponential in the size of image, because for each pixel we have to provide one integer value, and at the same time the output has structure. The structure is the following: adjacent pixels for a given image are likely to belong to the same class, like here. Other examples are ranking, for example. We call it a structured prediction problem because in this setting we usually predict a permutation, which is typically represented by a vector, and the support of this variable has factorial size, because there are factorial there is a factorial number of permutation. And another typical example is handwriting recognition, when we get an image of some handwritten word or sentence, and then we have to predict a sequence of characters. Here the output is exponential in the length of sequence, and the dependence is captured by the internal structure of language in which the sentence is written. So I want to underline once again the key aspects of these problems. We have typically a very large number of labels, or maybe not very large, but after all we really care about the number of labels. And in these problems, to deal with such a big number of labels, we usually introduce a cost which is sensitive to our prediction, and we penalize for different mistakes in a different manner. In this work, we consider a pretty exotic type of problems, which we call inconsistent. I will talk more on what inconsistency means later. So this work generalizes the results of the work of Anton Osokin, Francis Bach, and Simon Lacon-Julien, which was presented at NIPS last year. We provide some theoretical guarantees for this exotic case, and what is more, we observe that this particular case leads us to algorithms which are more efficient in some sense than the algorithms that are that exist for consistent cases. So that's all for the informal introduction, and now some notation for the problem. In this setting we get data points which are represented by an argument, and a label. So here I clearly distinct that labels can belong to a different set than the predictions we want to make. In some problems, this is the case. For prediction, we use the formalism of score function. So when we get an x, we compute a function f, which we call a score function, which outputs a vector that scores each possible prediction. So this vector possibly has an exponential size. Then to make a prediction, we find the component of this vector which has the best score. We denote this prediction scheme like this. And here Argmax means that we find a component of vector f, computed of vector f, that is the value of function f at x, that has the biggest value.
One question.
Yeah.
How the sets y and z are related with each other? Can we say that one set is almost richer or equal than another, or not?
Sometimes they coincide.
Yes, I understand.
It depends on the problem. In the one setting in which this will be important, z will be a set of binary vectors, and y will be a set of permutations.
So what is one?
You mean y is a subset of z?
No, they are completely different.
Uh-huh.
They have different nature.
Interesting. And you review this example, right?
Yes.
Yeah.
This is one of the most important examples in our paper. Yeah.
Is it correct that f with index y hat y is one-dimensional? So y
Once again,
is y one-dimensional?
Y hat.
we do not explicitly specify what y is. Typically,
But what is fy? Is it
fy is a component of vector, a
So
component that
y-
has index y. So
Y
we can-
hat is just an index of a vector.
Typically, we use a finite set of predictions, so we can put it to one-to-one correspondence to natural numbers, and then build a correspondence of predictions to components of score function.
in the case of image segmentation, y is y a label of one pixel or a labeling of the whole image?
It's the whole labeling of image. One labeling for the whole image.
So
It includes all values for each pixel.
So the capital Y is all possible labelings.
Yes. That's exactly the case. Sometimes we get score functions from the problem, and sometimes we try to learn the score function from data. And this is exactly the setting we considered in this paper, where we want to learn a score function from data. To do this, we consider a framework of population risk minimization. So we introduce LS matrix, which scores for true labels and for our prediction how good our prediction is. For example, this matrix can be the Hamming distance between two binary vectors if y and z are the sets of binary vectors. And then we choose f to be the function which minimizes this expectation, which we call population risk. That's it. This is not the only possible way to learn a score function. For example, we can do something like maximum likelihood estimation or variational inference, but in this case we only consider population risk minimization.
Can you give the examples in simple cases? Like if we
Sure.
learn linear regression, what is the optimal app?
The case of linear regression is not the case that we consider, because
Why?
linear
We can do
regression,
this. Consider all
deals
possible
with-
scores, which is the set of one regression label.
That is the classification problem.
we only consider problems where we have to make a prediction that belongs to a finite data set. So linear regression is not the case, but I can give an example of binary classification
Okay.
for So this is exactly the example which I was going to discuss on the next slide. But first of all, what is the matrix L for binary classification? This is a matrix that looks like this. We do not penalize correct predictions, and we introduce penalty that is equal to 1 for incorrect prediction. The risk we want to optimize in this case is just accuracy. That's it. But as you know, you can't optimize accuracy directly with something like stochastic gradient descent because accuracy is not differentiable. So here goes the next very important part of our framework. How do we actually learn these core functions? First of all, population risk is likely to be non-differentiable, so it may be hard to design practical algorithms, and at the same time it can be non-convex, so it may be hard to give some guarantees on the optimal value and optimization in general for population risk. So a typical workaround is to replace population risk with some auxiliary risk that we actually can optimize. In this work, throughout this work, we call such auxiliary loss functions surrogates. So the word surrogates in the title of the talk corresponds to auxiliary loss functions that we used to solve the original problem. It looks pretty much like the population risk, but we replace matrix L with some function f that takes as input the value of f and the true label. And then we learn by trying to optimize surrogate loss function. So in case of binary classification or classification in general, a very common surrogate is cross entropy. So you use this surrogate, and then for prediction you output a label which has the best score.
Well, here is the strange thing that you state the infinite dimensional optimization program. Because usually we say that let's take f of x in some family, like narrow networks with some parameters, and we minimize with respect to these parameters. But you say that instead we minimize over all set of possible functions.
I did not clearly indicate yet what f is. It's not the set of all possible functions. I have to make it clear. It's some set of functions which we use to parameterize core functions. And I will talk more later on what f could be. And it is really a very important matter in this work. A very important matter in this work. Anyway, so for classification, a typical surrogate is cross entropy. It deals only with such kind of matrices. Another example is a general purpose method called SSM, which takes an arbitrary loss matrix and uses this surrogate to solve the population risk optimization problem. So the first thing to ask when you replace one optimization problem with another is how these optimization problems are related. Because in practice, we want to be sure that optimization of surrogate risk leads to optimization of population risk. And to capture this idea, a notion of consistency has been introduced. It's somehow related to consistency in statistics. And in this work, consistency means the following. So if we optimize the surrogate exactly and find a score function which optimizes the surrogate exactly, then the surrogate is consistent if, in this case, the population risk is also minimized exactly. So,
And what is the relation with consistency from statistics?
Different convergence measures.
in statistics, you refer to limit in the infinite data limit.
Mm-hmm.
Here we use expectations, which work like infinite data limit.
Okay.
And so our estimator is the procedure of optimization of surrogate, and this estimator is consistent if optimization leads you to the correct estimation.
Okay, thanks.
I hope I made it clear, but I'm not really satisfied.
Okay, that's not so important actually.
So for example, the cross entropy I referred to on the previous slide is a consistent surrogate because it can be, for some reason, I will not elaborate on this.
For SVM, for structured SVM,
No.
for binary classification.
For binary classification, cross entropy leads to a consistent surrogate, is a consistent surrogate.
And is the proof easy or not?
It's pretty easy. You have just to connect accuracy for expected accuracy for infinite data to values of calibdivergence, and then write calibdivergence with cross entropy. It's pretty straightforward, but I don't want to confuse you with messy explanations. At the same time, so the consistency has been massively explored in machine learning literature, especially for classification tasks. There are much more general conditions for consistency for classification. Then there is a broader class of surrogates for classification that is consistent. And last year, Anton gave these exact conditions during his talk. And at the same time, also SSVM has been explored for some problems, and it has been shown that in some settings, SSVM is consistent, but in some settings it is not. Still, SSVM is used in practice.
Okay, one question. What about just binary SVM? Is it always consistent or sometimes it's inconsistent as well?
I'm not really sure.
It is consistent.
It is
It is.
consistent. Oh, yeah. So, sure. So, hinge loss satisfies the set of general requirements for consistency in binary classification. So if you want to answer a question of whether this surrogate is consistent or not, a typical way to go is to compute so-called calibration function, which is one of the central concepts of our work. And I will give a pretty thorough introduction in calibration functions. So first of all, some notes. I've been hit by electricity at the same moment.
So it's because of you.
It's inconsistency. And this is consistency.
Okay. So first of all, an intuitive explanation of what calibration function is. So this is a sort of function which gives us the following guarantees. Recall that our calligraphic R is used in my talk to represent expected loss. Here it's an expected surrogate loss, and this is an optimal expected surrogate loss in the optimal point. So calibration functions gives the following guarantees. If we optimize surrogate up to this accuracy captured by calibration function, then we can guarantee that we've optimized the population risk up to this accuracy. Here epsilon is an argument of the calibration function, and here epsilon is just a parameter on the right hand side of the inequality. So basically calibration functions relate surrogate losses, guarantees for surrogate losses, and guarantees for population risk. In our setting, it's a function which depends on the choice of surrogate, the loss matrix, and set of score functions as parameters, and it looks pretty much like this. If you want to optimize your, once again, your population risk up to this accuracy. You just have to compute the calibration function and optimize surrogate up to this accuracy.
So do I understand right that surrogate loss is consistent if h of 0 equals to 0?
Not really. Because there can be cases like this. So, in this case, the limit from the right is not 0. And for this point, we can have guarantees. For this point, we can have guarantees. And for this accuracy population risk, we can have guarantees. But if you get into the details in the definition of calibration function, in this case, when the calibration function is 0, you can have no guarantees. By the way, look, we have h equal to 0. This is an impossible configuration because we can't optimize this guy to be even smaller than the optimal value of.
And we're going to optimize it to be the optimal value.
We can optimize it to be, but the condition will not hold. 0 is not less than 0. So in this case, we have no guarantees. But you're pretty close to the truth. Surrogate is consistent if and only if for each positive value of epsilon, the calibration function is positive.
And goes to 0.
And goes to 0, yeah. Sure.
What do you mean by goes to 0?
It's not a constant for it.
It's a very, very strange
It
situation.
should be finite. It should not be infinity, but like
Maybe it may be not 0.
so.
It's very.
For instance, h of epsilon, for instance, is just equal to 2 for all epsilon.
Okay, it may be the case that we did not really optimize the surrogate, but somehow it turns out that even in this bad situation, the population risk is optimized.
Always,
It
right?
can be constant because we have our star. We have our star, which is an infimum over all possible f's, so it should be a 0 somewhere, in the limit at least.
I think that by definition h of 0 is always 0, but like this doesn't really matter. It doesn't mean consistency.
Let's look at this later, because next time I'm going to construct the calibration function step by step to give an explicit construction which we use for analysis in our work. So I'll define calibration function in 3 steps. First of all, I introduce conditional losses. A conditional loss, actual and surrogate losses, are defined as follows. So a function which takes our prediction, some vector which we think of as prediction, and some distribution Q, which we can think of as conditional distribution of labels given x. And for one particular x, for the prediction which we made for this x, and the distribution of labels, we compute an average loss. And we do the same thing for surrogate. Here are the conditional losses. These conditional losses can be used to rewrite expected risks.
Just an expectation over Q. It looks like an expectation.
It is. It is an expectation over Q. If we replace for our actual data distribution Q with marginal distribution of labels, given x, and compute these quantities, we'll have population risk and surrogate risk.
And from where we will take this PD? how can we compute, or how can we find the P of D? So this is the distribution of all possible values given X, right?
Yes. It's if we have data distribution as some distribution as an object, there exists a conditional distribution, and this is the.
Okay, so we can compute it, but only in theory.
This is just an introduction to a theoretical tool. I'm not speaking about any explicit computations of these quantities yet.
Okay.
But nevertheless, we can compute these quantities using the introduced conditional losses.
And what is bold F?
It's a very nice question. I forgot to clarify it once again. So these functions are defined for some vectors. But when we compute population risk and expected loss, we want to compute it for our predictor. So here f is the function, the core function we use. F
Maybe these are the values of the score function for all objects in our training data.
you can think of it like this. It's the function which takes x's and then computes a denote function like this. To make a distinction between vectors here and functions. The value of function at point x is denoted like this. Maybe not the best notation. These are different objects. Vector here, function here, as a function is an object mathematically, and the value of function like this.
Good.
Now we can go even further and introduce the excess. So we've already defined it. We've already defined conditional losses, and now we can compare it to the best value of loss we could have obtained. For actual loss, we compare it to minimum over all possible vectors, all possible predictions we could make. And this function, which takes a distribution and a vector, is defined like this. At the same time, we define excess for surrogate loss like this. And it is very important to know that here we take minimum over a different set. So f here corresponds to possible realizable values of functions. So such vectors for which exists a function and an argument for which we can make this kind of prediction. So we compare our surrogate loss to the best prediction we could have made using our family of predictors.
Does it mean that in the first case, if we use, for example, Hamming loss for classification problem, our f hat is just the such kind of vector which always predicts the right class label? I just want to get some intuition.
Let's try to think about this. So if Q is a divergent distribution, which is concentrated in one vector, then this is true. We give the best score to the correct prediction.
Okay, and the Random distribution Q that exists an optimal vector f hat, right? Which minimizes this loss, and this is it.
Okay.
Maybe we could consider, say, binary classification case, just to for more intuition.
Let's try.
So for binary classification, Q is just distribution of a binary label, right? So this is simply Bernoulli distribution.
Zero. So I write down the definition of conditional loss for binary classification.
And for this kind of loss, right?
For
For-
binary classification.
Mm-hmm. Maybe then it should be Q0 times
Is it correct?
spread F equal to 1 plus Q1 times spread F equal to 0.
Yes.
Mm-hmm. This is it, and you may also use the fact that Q1 equals to 1 minus Q0.
Mhm. We can also rewrite the indicator.
Mm-hmm.
Also on the indicator like this.
Oops.
Let's go.
Okay, and what would be the optimal value of F if we're given some Q0?
Probably it would. My first guess is that F would assign a better score to the class which has higher probability.
Would assign what?
Higher score to the prediction which has a
Mhm.
higher probability.
Well, this sounds very reasonable.
In this case, imagine
So the
that-
minimum is not unique.
yeah, it's not unique. It may be the case.
I still didn't understand.
But for our phi, for surrogate loss, it seems like it would be a unique minimum with plus infinity for true plus.
But could you give us at least one example of F hat, which is the optimal for such kind of loss function?
So let's assume that Q0 is greater than Q1.
Okay.
Then F hat can be a vector that looks like this. So our prediction is 0.
Mm-hmm.
Yeah.
And the conditional loss will be Q1, just Q1.
Mm-hmm.
In the other case, for other prediction, 0, 1,
Yeah.
the conditional loss will be Q0,
Q0.
which is bigger.
Yeah. And this is the only option, right? Because we define function L small as a function of a large from red of F.
So the minimum can be achieved at different points here, because we have a complete freedom of giving different scores here that have right order. But the value of minimum is unique. So, these excesses can help us to compute the excess of expected risk for the loss function and for surrogate loss function, just like this.
Change minimum and expectation
Mhm.
because they are in different sets.
Yes. So this is all for the step 2. Any questions? Let's proceed to the final step. Here's the definition of the calibration function. We've already introduced all the quantities in here. Excess for surrogate loss, excess for actual loss, and a class of score functions. Q is assumed to be a distribution. So what does it say? We look for the prediction for some distribution for which our surrogate loss is the most confident. It has the smallest value. But at the same time, while we're confident about the surrogate loss, the actual loss is bigger than epsilon. It's not small, it's bigger than epsilon. And so this is the definition of score function.
And if, for example, it happens so that this minimum was achieved at 0, I mean that this minimum equal to 0, this means that our surrogate function is inconsistent, right?
Yes.
Good.
So know that by this definition, it trivially follows that if you plug excess of actual loss as an argument of calibration function, then the value of calibration function will be smaller than the excess of surrogate loss. Look,
Why so?
if you replace epsilon with this excess, this restriction will be always satisfied. And since this is the minimum is smaller or equal to just an arbitrary value. A trivial observation.
Yeah.
So now we, in one slide, will prove that this definition of calibration function that we've introduced gives us a way to provide guarantees for the relation between surrogate loss and the actual loss. Here's the proof. Step by step. We assume that we've optimized the surrogate up to this precision, which we write as the value of calibration function. So again, as we've already agreed upon, this inequality holds. It really follows from the definition of calibration function. Now I will also assume that calibration function is convex and strictly monotonic. Just for a moment. It's monotonic by definition because epsilon is just a parameter, and if you make epsilon smaller, the set of our restriction increases. It's monotonic, but it may be not strictly monotonic. But I assume these facts. So we have this inequality. We can plug in the conditional likelihood here and average this inequality. So this is what I do in these two inequalities. The average of calibration function with Q replaced by conditional probability. And this is the difference between surrogate risk and the optimal surrogate risk. Also by definition of excess, trivial. By our assumption, we also have that this difference is smaller than the value of calibration function. This is the assumption on line 1. And at the same time, since I've told you that the calibration function is convex, we can switch places. We can switch expectation and calibration function here, and move expectation inside the calibration function, and then use the definition of excess for actual loss. And this is just the difference of risks. Now here comes the part where I need strict monotonicity of calibration function, because I want to invert this inequality that calibration function of this difference is smaller than calibration function of epsilon. If I can get rid of this function, then I will get this inequality. This is actually the thing I want to guarantee.
I have one thing that bothers me. If you assume strict monotonicity, this means that you cannot get this situation you draw here, right?
Yes.
That you have plateau at 0 and increase up to some point.
It means that if this situation occurs, we can still use the same argument for this part, but we cannot provide any guarantees using this argument here. It's the way calibration functions work. We don't have any guarantees at this part. So it is very natural.
Okay.
What about the assumptions on convexity and strict monotonicity? If it is not the true for the actual calibration function, actually we can replace a calibration function with a convex lower bound that is monotonic and use this same argument for the convex lower bound for calibration function. So it means that we cannot use the exact calibration function, but we still have a way to provide these guarantees using a convex lower bound of calibration function. And once again, this is an illustration of how calibration functions work. Great. Any questions?
If, for example, your function h is a logarithm,
Is a logarithm.
how do you lower bound it by convex function?
But it's not convex function. It's logarithm.
Yes, but Kirill said that if you have a non-convex function, h, you can lower bound it by a convex one.
First of all, recall that, okay, our calibration function is logarithm. Fine. First of all, recall that our loss matrix is finite, and since it's finite, there are only finite possible values for loss. So,
You simply are bounded by a linear function.
There is an upper bound on the expected loss, after which the calibration function is infinity.
we can. What I'm trying to say is that we can still build a convex lower bound that looks like this. It's
some
very
interval.
on some interval.
But that's
We're-
not of
we're-
interest.
We're interested in small values of epsilon and some small values of this optimization error. So this would work fine, but at the same time, it is not a very good solution. Why? By the definition of calibration function, I should have told you that even earlier. The bigger the values of calibration function are, the better is the situation for us. Because if the values of calibration function are big, it means that if we want to provide guarantees for example, this particular value of optimization accuracy, then for one calibration function we may have to optimize up to this accuracy, and if for another calibration function the value is bigger, then the requirements for optimization accuracy are much lower and can be obtained at lower price. So the bigger the calibration function is, the better, because we provide stronger guarantees for the relation between surrogate loss optimization error and actual loss optimization error.
Well, it seems that the logarithm is a good case. It's like a superlinear convergence.
Let's put it this way. I've never seen a calibration function like that. And then if you show me one, I can work out the details, how to make the...
Yeah. We can submit another newspaper. And it is usually not the case. Maybe,
So it means that your optimization is actually inefficient for very small epsilon.
Yes, it is. It means I will also talk on that later, because in the case of structured prediction, know that calibration functions are a valid concept for any machine learning problem. So in the case of structured prediction, this case when the value of calibration function is low becomes disastrous, and optimization methods can be very inefficient. So how do we use our framework to provide any guarantees that statistical learning theorist would be interested in? So in statistical learning theory, the guarantees usually look like this. So to obtain this accuracy on the population risk, you would need a data set of this size and exact optimization. For example, Or you would need to make this number of steps of learning algorithm. And in our framework, we only look at calibration functions. So how do calibration functions help to provide these guarantees? Well, they can be used in conjunction with results from optimization versus statistical learning theory to provide guarantees for population risks. The general framework would look like this. First, we choose some result to give a guarantee for an upper bound for this difference. For example, in our work, we use results from stochastic optimization and make statements like this to optimize this difference up to this accuracy. We need X steps of stochastic gradient descent. For stochastic gradient descent, we don't need to work with finite data because we assume that stochastic gradient descent always gets samples from the actual distribution. And this is the way we provide guarantees for optimization quality of surrogate risk. Then, using our results about calibration functions, we can replace this difference in the statement with this difference in the statement. And after all, we would get a statement that looks like this. After X steps of stochastic gradient descent, we get such a guarantee for population risk. And recall that steps of gradient descent, they have one-to-one correspondence with the size of data we need for optimization. It may be not very efficient, and maybe some results for finite data sets can provide better guarantees. Still, we have some guarantees. Maybe reusing of data can increase efficiency of data.
But is it true only for the training data? Or we assume that we're making just one pass through the data?
It works like we make one pass through the data, and we choose the side of the data set.
Yeah. Okay. So the stricter is our requirements for the accuracy, the larger training data we need to have.
Sure. I will not give explicit estimates for the size of data set, but you can look it up in the talk from the last year. We can obtain that. Another important thing I have to clarify that we do not consider in our work an arbitrary surrogate. We consider so-called quadratic surrogates, which looks like this, and it has very nice properties from theoretical point of view because you can prove a lot of stuff about the surrogate. But let's discuss why the surrogate helps us to optimize the population risk. Intuitively, we reduce optimization of population risk to regression over the columns of loss matrix. We try to predict, given X, the column of loss matrix for label Z. So how can we use this column? If we've successfully managed to predict the column, we can then compute, we predict minus the column. And then
Minus the column, yeah.
Then we output the prediction, which has the best score. And it means that this prediction has the lowest value in the column in the loss matrix. So we sort of try to give predictions which have the smallest value for loss when we train using this quadratic surrogate. Is it clear? I'm not really sure.
Well, the 2 points in intuition part are clear, but I'm not sure that why quadratic function is important for that. I would assume that there are many other functions which possess these properties.
They possess this property, but so the main reason is that we can explicitly compute excesses for quadratic surrogate. The excesses I defined previously for conditional losses, and using these excesses we can compute the calibration function. Because for quadratic function minimization, we can find the actual minimum and then compute the value at the actual minimum.
Okay.
This is the reason why we only work with quadratic surrogates.
That was clear.
The nice property about the quadratic surrogates is that it is very easy to guarantee consistency for quadratic surrogates. You would need only to guarantee that this function can predict the value of loss matrix column. It can be easily guaranteed. Bad part about this surrogate is that it's not really a surrogate you would use in practice for training your neural network. It's a kind of theoretical surrogate which is very appealing for theorists, but kind of unnatural for machine learning community. For practical science. Okay. I think I have to also say that such kinds of surrogates were studied from a theoretical point of view in the general setting, first in the work of Ciliberto in 2016, right? Not exactly these surrogates, but very similar ones. And also this particular surrogate has been studied in the work of Osokin. So let's try to compute for specific loss matrices the value of calibration function. This picture represents a loss matrix that penalizes mistakes with 1, and each mistake penalizes the same way. And for the correct prediction, it says loss is 0. If you use quadratic surrogate, this particular loss, and pose no restrictions on the class of score functions, which means that the score function can give an output for some x that can be an arbitrary letter in RK. No restrictions on the class of loss functions. Then the value of calibration function is this, and it is not lower 1. This is the exact value, maybe up to a constant. And it means that, well, okay, this is variable. But in the denominator, we have k. And I have to repeat it once again. K is the cardinality of the set of our predictions. And for various problems, this size is exponential. And it means that we have to optimize surrogate loss up to exponential accuracy, to make the accuracy exponentially small, to obtain some decent guarantees for population loss. So this calibration function tells us that it is a very poor choice to train problems with an exponential number of classes using this kind of loss. It's impossible from optimization point of view. Okay, maybe we can add some structure.
But I think this is very reasonable and it correlates with the common sense.
Don't have such a nice common sense. But I can disagree with you, but because I know this is a fact. Why is it natural from?
This is unnatural.
Unnatural.
Such kind of 0-1 loss is very unnatural for the case of exponential large number of classes.
Yes, it is very unnatural. Sure.
And this is mathematical evidence of this fact.
Yes.
So it's
I agree with
extremely
that.
hard to optimize such kind of 0-1 losses with exponential number of classes.
Maybe we can introduce some structure.
Sorry, I can't stop myself, but like add that comment about latest research here, that exactly the same fact holds for not for quadratic loss, but for log likelihood objective. So if we consider 0-1 loss and optimize with log likelihood, it's like the behavior is the same. It's like k in the denominator. It means
Yes,
that
but this is a property not of surrogate loss. This is a property of initial loss, of loss function. 0-1 loss function for exponentially large number of classes is very unreasonable.
and
Yes, it is unreasonable. We have evidence only for quadratic surrogates. And Anton says that we also now have evidence for log likelihood.
Okay, and this doesn't contradict what I thought.
yeah, that confirms that
Mhm.
this is there is hope to generalize this fact to more cases.
Good.
A very trivial way to introduce structure to this problem. Let's let's use block structured loss matrix, which makes no penalty if we predicted a label in the correct block, but penalizes in the same way if we made a prediction in the wrong block. So effectively, this is just, in this illustration, depicts four-class classification. This particular matrix is a matrix for four-class classification. Still, if we compute the calibration function for quadratic surrogates for this kind of loss matrix and for score functions with no restrictions, the result looks like this. Again, k here, and s is the number of blocks. So this factor is for the case of 4 blocks, it's just
S is the size of the
5/4.
block.
Size of block. Oh, sorry.
Size of block or number of blocks?
Okay.
This is different.
Size of block.
Size of the block.
Sure.
So,
Wait, if you increase the size of the block up to the maximum,
yeah,
it goes to 1, so nothing changes.
Yes.
but there's k in denominator,
Oh yeah, right.
not k squared. It's a
It was a
center
k
rule.
squared on the last slide.
Wasn't it?
It's k.
And on the last
So
one,
you
the previous
essentially
one?
recover the previous case.
Okay.
If s is equal to k, the formula, so you should have an inequality. It's not an equality.
Okay, maybe I'm wrong here.
But
Nevertheless,
what do
we're-
you mean? Well, that's the exact result.
If s is equal to k,
Yes.
this number do
So-
not equal to the previous one.
probably an inequality has to be here.
No, like those are both. I think S just it can't equal to k. It breaks the limit.
No, if s is the size of the block, the size of the block can be equal to k.
Oh yeah, you can't have one block.
Yeah, at least 2.
Yeah, but if s equals to 1,
S equals to 1. Yes. If S equals to 1, it should be. I think you got 2 somewhere. It's just constant factor 2. And then
No, but again, s is the size of the block, not the number of blocks.
I
Just to
don't think so.
clarify.
I mean, if
Is it
s
number
is
of-
equal to k, then we don't penalize anything at all, right? So, it doesn't seem so. I mean, if s is maximal, is like infinity, then you treat infinite number of classes as the same. Essentially, do not penalizing for any mismatch. So the bigger the size of a block, the smaller should the h be. Whereas here we see that
I'm not sure. So let's consider some limit case. There's one block and another block. So this becomes exactly equivalent to 2-class classification problem,
yes.
right? So what will we obtain then? So the size of the block equals k over 2,
Over 2.
right? K over 2.
So this fraction is almost 1,
Yeah.
and this is the same.
But then
I'm not trying to convince you that this is a good value of calibration function. Don't expect anything good here.
I think what is it, instead of looking at this formula, we could think about what is actually going on. When we introduce these blocks, we essentially just scale k divided by some factor. If we have, if we previously had one class in each block, and now we have like s classes in one block, then that should be sort of equivalent to dividing k by s.
It should be, but this
So-
is not the case for
Yeah. So
this
probably this
particular
means that
calculation function.
that this surrogate function is not good.
Something is missing.
Because it's quite clear that the quantity should be bigger, but it's not actually.
It is not.
Although the limit case is when we have just two-class classification problem. We should have much better results here, but we do not.
Mhm.
And probably now you'll show us the way out.
The very important way out is to explicitly introduce some restriction on the family of score function. For example, in this case, we may force score functions to output the same scores for all the classes in the block. And this would fix it. So in general, in our work, we consider the following predictor functions, which are typically factorized using some fixed matrix and a function we actually learned. Recall that our prediction, our score function has an exponential number of values, and we can't actually deal with such functions directly in practice because we can't store an exponential number of values on computer. But if we fix some design metric set, we can work with low-dimensional functions, and then for prediction compute f times theta, and then search for the biggest value. Or efficiently, you can somehow choose the value, the best prediction, knowing theta, but not computing the whole matrix product directly. We use this factorization and only work in practice with low-dimensional functions, which we then multiply by f to get score functions. So this is the kind of restrictions. For example, if you want to restrict score functions to output the same values for each block, you can use this kind of score function. In the previous example, we'll have a four-dimensional function theta x and matrix f, which looks like this: once, and zeros elsewhere.
So in fact, the behavior of the score function is completely described by the behavior of theta of x, which is of low-dimensional vector, right?
Sure. And this is the thing we can work with in practice. I did not provide the value for the restricted scores exactly, but I want to say once again that if you introduce a smart restriction in the previous case for block matrix, you would get exactly what you want. Calibration function for the smaller number of classes, for the 4 classes. And the theory works well in this case, if you introduce the restrictions. So the general result obtained by Anton looks like this. First of all, this result works only in the consistent case, where we choose matrix F to have a pretty big span, which covers the span of columns of matrix F. This is the necessary condition for consistency, because in this case, for non-parametric theta, we still can predict any column of loss matrix if the span of F is bigger than the span of L.
It's a sufficient condition for consistency.
It's sufficient. Okay. It's a sufficient condition. If we have this condition, the calibration function can be bounded from below, like this. So what do we have here? Still epsilon squared, and probably it comes from the nature of quadratic surrogates. Still this factor 2 by k, which is exponentially large. But now we have this quantity, pi, which depends on the classes. And this quantity is defined like this. We take two vectors that have zeros everywhere except for index y1 and y2. We compute the difference and then project this vector on the subspace defined by our score parameterization. So the span of that matrix F. And if F is very big, this is just 2. Or it's 2. If F is small, this quantity can get smaller because the linear space gets smaller and the projection on this linear space can get smaller. And in practice, we really observe for actual practical loss function that this happens. And we can balance out this exponential quality with an exponentially small projection on the score subset.
But if you minimize the whole expression with respect to y1 not equal to y2, it's equivalent to maximizing the denominator,
Yes.
right?
So we sort of we maximize the denominator and search over various parabolas with different slopes. A parabola with the worst slope that is possible.
Good. Yeah.
This comes from the way we compute the lower bound for calibration functions. So the calibration function is defined as optimization problem. It's a non-convex optimization problem, which may be nasty, but somehow you can split this optimization problem into an exponential number of convex optimization problems, which each problem corresponds to a couple of labels, or each problem corresponds to a couple of labels. And then you can solve a convex optimization problem for each couple of labels, and then find the worst solution. This will be our calibration function. So this is a very nice result if you have a low rank loss, because if your loss is low rank, then you can take a very small f, get a very small projection, and obtain very nice guarantees for calibration function. For example, if you deal with Hamming distance, the sufficient rank of score matrix is the length of binary vector, which is logarithmic in the size of possible prediction. And you get not an exponential, not k, but log k here, which is just the length of vector. Nice result. But, so we observed that the smaller f we take, the better guarantees we obtain. But still this work only deals with the consistent case. And in the recent work, we were asking the question, is it possible to get any guarantees if you break this condition and go below the consistency? As it turns out, it's possible. So the result, we obtained, replaced the consistency condition which relates the spans of L and F with, it omitted this condition and replaced the lower bound with this kind of lower bound. Still we have 2k by pyy, it's the same as in the previous case. Still we have the minimum of all possible pairs of predictions. But now we have a different type of quadratic function. So here we have an offset which we denote by xi. And for this offset, we have a function which looks like this. If epsilon is smaller than the offset, value is 0, and we're in the inconsistent case. But if epsilon is bigger than the offset, we have this nice curve. And know that while for the previous results it was necessary to provide this kind of guarantees. In our case, we can take arbitrary matrix L and an arbitrary matrix F, and still our lower bound will be valid. It may be very poor, and if F is completely unrelated to L, this offset will be very bad, and we will have something like this. No guarantees for almost all epsilons, but still we'll have some guarantees later. Maybe they will be very bad. This lower bound is pretty general. And know that it corresponds, it coincides with the lower bound obtained by Anton in the case when this condition is satisfied. Because the projection on F times L transposed is just like, so I know what I'm trying to say. Projection makes no difference if this condition is satisfied. So we compare this quantity with this quantity. And if the span condition is satisfied, then we'll have this equality. And the offset we have zero value, and the lower bound will be the same as in the consistent case. By the way, in our work we found even more ways to balance the value of offset and the slope of this curve. And these ways can give you even tighter lower bounds, but I will not talk on this during this talk. You can go and read the paper for the details. I hope it will be on arXiv very soon. So now we can go beyond consistency and take matrices F that are even smaller than the span of L, and it gives us a very nice opportunity to make this projection even smaller than it was in the consistent case. And it means that we will obtain even bigger slope
Here.
And we have
At the expense of this axis.
at the expense of this axis. We can have better guarantees for some epsilons, but at the same time we lose consistency guarantees. But still, the argument for monotonicity, for guarantees for calibration function still works on this segment. And there are still guarantees for population rate. So how do you get a paper accepted to NIMS with no experimental results? So
Guess?
how do you? Not really. So still we had to verify that our theory gives some valid results for some practical problems. And it was very important, and this type of loss was our two-mode Gaussian experiment. This type of loss we considered. It's called tree structure. This is a very simple example when the tree have depth 2. So we try to make a prediction, and the labels form some kind of hierarchy. For example, we can differentiate species and breeds inside the species. We can put 0 penalty if we predict species correctly, breed correctly. Some penalty if species is predicted correctly, but the breed is predicted in a wrong manner. And we can introduce the biggest penalty if the prediction is completely wrong. So this kind of loss corresponds to the mixture of 0-1 loss and block 0-1 loss. From one hand, it has structure, and we have to obtain some better guarantees for this kind of loss. But at the same time, this kind of loss is a full rank loss. So if we want to use the theory from last year, we would have to use the biggest matrix F possible and obtain the worst result. But this kind of loss for depth 2 was considered in the paper, and it was shown in the paper of Anton, and it was shown for this picture that you can still have better guarantees at the cost of consistency. So they observed for this particular loss this kind of behavior. We also checked our lower bound in this case. It coincides with the lower bound, with the exact lower bound computed previously. And also we generalized this kind of loss to tree structure, where we have some restriction on the type of trees, but in general, leaves correspond to classes, and loss is computed as the distance between leaves in the tree. For this kind of loss that can be used for classification, we computed the lower bound for calibration function and still observe the same result in more general case. We have some offset that makes consistency worse, but for some cases the calibration function is bigger than in the consistent case. This is not. This is just an illustration. This is not an exact value for some loss, but possibly you can construct a loss that has these curves for consistent and inconsistent case. So this is a toy problem because in practice we're limited to the number of classes, and it is very likely that the number of classes in our data is exponential. Probably it's like thousands or. Let's move on to the exponential sizes. This is sort of least of our work so far. Okay. Next thing we considered is the Rankine problem. This is the exact problem for which I separated labels, data sets for labels and for predictions. There are various losses for ranking, but in our work we considered a type of loss which is called MAP. The setting is the following. In the training set we get search queries as inputs for predictor, and as labels we get relevance vectors. These kind of vectors are easy to assess. You just ask a person to mark whether this document is relevant or not. So this is the kind of data we have. A huge binary vector that represents relevance of each document in the database. And our prediction has to be a permutation which favors relevant documents or non-relevant documents. So the loss matrix in our case has size, you can guess, it has size r factorial over 2 to the r. The number of possible predictions and the number of possible labels in the training set. MAP loss looks like this. We compute on average how many relevant documents we favored over non-relevant. So this is the sort of loss. I'm not going to give more details on this. It's defined like this. Why are we interested in this loss? Because it was shown that this loss has a low rank structure. In fact, you can rewrite the loss using some permutation qualities, permutation facts, like this. And what is interesting in this expression is that this expression gives a low rank decomposition for this particular loss, and this loss can be presented as a product of some matrix, and this matrix, which has size r factorial over just something like r squared. R squared is much lower than 2 to the r, and this is the kind of thing we can work with. We can predict r squared scores for each query. It's pretty big if we are Google, but okay, let's suppose that we can do it.
One question: how did you get this expression? Is it non-fact?
This expression? you just have to rewrite sums and change the order of summation by switching from natural indexing to the permutation of indices. This is a pretty trivial fact, but it is important for introduction of lower rank decomposition.
Sure.
It's lower rank. We can use this matrix gives us a way to build a consistent quadratic surrogate because we can use R-squared dimensional scores. But the sad thing about this particular loss in the consistent case is that the prediction, that maximization over the components of f theta is a quadratic assignment problem, which is known to be NP hard. So not only we have to compute Boolean by Boolean vectors for our documents, restore Boolean documents, but we also have to solve an NP hard problem to make prediction. And this is not the way an efficient search engine would work. So in work in which this loss has been considered, they also introduced another matrix, which we call f-sort, which has even smaller rank. Now it's linear instead of quadratic, and it has these values. In the paper of Roman Zaswami, they show that if you put some assumptions on the data distribution, this loss is consistent. But in general, this loss is inconsistent, but at the same time, well, the previous loss required solving NP hard problem. This loss reduces to sorting for prediction. You just have to sort over the values of your theta of x, and then output the permutation that you've obtained after sorting as an output.
What is sigma of p?
Sigma of p is a value of permutation sigma. Recall that we index, the first index is the set of our predictions.
Right.
In this case, these are permutation.
Uh-huh.
For a fixed permutation and index p, we compute the permutation of p.
Uh-huh. Okay.
It's a nice result for some assumptions on data distribution, but no results in the general case, but at the same time very efficient prediction algorithm. So we computed our lower bound in this case. We computed all the quantities needed to compute the lower bound, but I'll be honest, we didn't manage to solve the minimization over all possible predictions. Nevertheless, we computed the lower bound for some cases, and the values look like this. The lower bound for the inconsistent case is the blue dashed line. It's 0 up to this point, and then it rockets up. And at the same time, the lower bound for consistent case looks like this. It's lower than our lower bound. So if you want to obtain this kind of accuracy, you would have to optimize this thing and get a nice prediction algorithm. And what is more, if you put no restrictions at all on the score functions, you would get this kind of lower bound, which is even worse. This is the thing we've already observed earlier, that the structure of score functions is very important.
And what do people usually use as the surrogate for this problem?
I'm a theorist. You chose a wrong kind of person to ask. I don't really know.
You should ask Yandex. They do review something about it.
I don't know. Since that they differentiate MAP directly, no?
Well, some people try to do this, you know, with neural networks they differentiate everything, but like they have no guarantees.
So
they use boosting, this like boosting of trees.
the conclusion slide. So what have we done? We introduced some guarantees for the worst case analysis for structured prediction for inconsistent problems. The thing we observed and captured numerically is that the choice of score functions really matter, and also we captured the fact that you can even sacrifice the consistency to obtain better guarantees. Instead of these lower bounds, we obtain this kind of lower bound. Previously, only this kind of lower bounds for inconsistent case existed. And what are the future directions for our research? Probably some restriction on data distribution could even improve our lower bounds more. As it was data distribution assumptions improved the results for ranking in a different setting. And we hope that maybe it would improve the results for our lower bounds. Also, we really would like to go beyond quadratic surrogates, because quadratic surrogates are not the surrogates you would use in practice. And we want to, after all, we want to design theoretical guarantees for the thing you use in practice. And also, we also would really like to explore more higher rank losses, which were unable to deal with, impossible to deal with in consistency setting, but we can work with them in our framework. That's pretty much it, but also I would like to add, we don't really have to be scared of theory. Although the framework I've introduced is very non-trivial, people had to work for years to design this framework. The results we've obtained are not very complex. We just solved an optimization problem better than it has been solved previously in the literature, and that's how we obtained our results. So theory is not really scary.
Okay, let us thank the speaker. So, any questions? Oh, I assume that. Yeah.
I have one about machine translation. Machine translation, people usually report blur score and optimize something like log likelihood. Oh, sorry. Can we say something for this case about consistency?
We did not try anything at all in this project, but I believe this is the kind of question which Antoine tries to explore in his work with Irina's problem, right?
No.
From the
I think that the blur is too hard. We don't even know if it's a rank or not. So it's like, and also like in that particular problem, it's very important to output sentences of different length, and this like this breaks our assumption on finite outputs. So there is infinite number of possible outputs of any length.
You can bound the length.
Yes, okay, but like it's not helping. We can, but like it's not really helping. So anyway, like we can't really. We would love to say anything about blur and like destroy all the current machine learning, machine translation algorithms, but we just can't. So sorry. If anybody wants to try it, well, we can try to help. Like, I'm not sure if we can.
Great. Well, I personally, well, first of all, I'm very glad that you found this theoretical branch of research, and with your success at NIPS, I personally felt myself hopeless engineer while listening to your talk, but at least I managed to understand something. Not everything, but probably the most of material. So, okay, let us thank the speaker once again.